Hey, what's up, guys? Okay, so in this video, I want to keep talking about the BQP complexity class. So basically, this video that our goal is to show this is true. So B subset BBP, BQP, and BP, and PSPACE and XP. Okay, so one from let's say the comma fact, which is easy to prove, is this, right? Because right, this one is like trivial, right? Because if you have polynomial time algorithm that you will always have the polynomial verifier, right? Because verifier can take whatever witness and directly solve P. And for NP, right, you can consider the Boolean circuit and ask whether there is a solution where such f of x equals to 1. And right, for this one that you can solve in a P space because you can enumerate all the possibilities and enumerate all these possibilities without like you can reuse a space, right? Because you only need you have two to n choice, right? You only need like n space, right? N space that you can store all the results, and then maybe some extra space to compute this, right? But still in poly n, and the P space is similar in the XP that you can show this. Okay, and we know that this P is different from we know that these two are different, right? This is called the time hierarchy theorem. If you're interested, you can check out my other videos. And okay, so our goal is to show this in this video. Okay, so mainly will be the BPP, the BQP. Okay, so let's write down the fact. Okay, so we already have this, and yeah, okay. So P, right? P is polynomial, the problem that you can solve in the polynomial time. BPP is the problem that you can solve in the polynomial time using the random bit, flip random coin. And since right, you have at most a polynomial time, so you at most can use the random bit polynomial time or polynomial times. Also, this one is very simple. This one just skip the randomness. Okay, so for this one, that BPP is a subset of BQP, right? In order to do this, you just need to show that the coin flip can be simulated. In a quantum computer. So it's very simple, right? You can just use a hard market, or somebody give you the 0, or you prepare some state, which is a spin up, and then you measure into a plus or minus 1 eigenspace. So basically, you measure x. Okay, so this will probability half. So each coin flip can be simulated using a single spin or single qubit. Just change another basis. Okay, so whenever you have spin, then you can change into BQP. Okay. And also for this one, that the PP, right? There's a complete problem for PP. Basically, you can take this, and you ask the whether the number accepting path or a number of x such that f of x equals 1 is greater than 2 to the minus 1. So it's like half of that, right? And for this one, that you can still use the same way, right? You can just compute all the results and store. You only need the polynomial time space to store and check whether this is true. Okay, so PP in the P space. So the only non-trivial part, probably the most non-trivial part, is this one. Okay, so it's this one. This is the same as this is the same as hard as you can check that there is a proof for NP is a subset of PP. So you need to like think carefully and try to like write down this proof. And okay, so before we do this, let's doing the 3-step, right? So I can try to show first I can show that BQP is a XP, and the second one that I can show that BQP is a subset of P space. So actually, this one already requires some work. Basically, it's use the Feynman integral. And for third one that we want to show that BQP is a less of PP, that you need to use a universal gate. And this one requires more detailed results, more technical skill. And okay, so this is our goal. Okay. So let's say proof for this one. So first one is BQP subset XP. Okay, so this one is like trivial, right? The reason is that you can just write, right? Because you can imagine that BQP is something start from 0 to the n, and using some unitary, a lot of unitary, and however you do measurement. Okay, so for each step that you can write down all the unitary, right? So it's 2 to the n, 2 to the n, so it's 2 to the n, 2 times 2 to the n complex number, and the 2 to the n times 2 to the n complex number. So you can just use the exponential time to do all the complex number multiplication. So you can solve this problem in XP, okay? Because you at most have like poly n gates. Okay, so you can totally easily check these are in exponential, right? Because this guy is exponential, and total poly n gate. So at most poly n times exponential. That's it. Okay. So this one is like a simple proof, just by definition. Like any quantum computing, the BQP is always in the XP. Okay, so second proof is that we want to show that BQP is in a P space. Okay, so this one require a little bit work using a Feynman diagram or Feynman sum of the history. So Feynman integral, or basically the definition of quantum computing, quantum mechanics. Okay, so required remember there's a universal gate. So one is a Hadamard gate, one is a Toffoli gate or CC0 gate. So basically these are Econ 2 qubit, and these are 3 qubit. And then we only need the polynomial n of all these gates. Okay, so if we only care about the final results, right? Then they say our initial is psi 0, or is c to the complex space, and then with q to the n. So q to the n is poly n. So it's some polynomial of n. Right, you start with some polynomial n of length, polynomial n qubits, and you have your final state size x un minus 1, un minus 2, up to u1 psi 0. And then all this u I belongs to either Hadamard or CC0 gate. So each ui x at most 3 qubits. Okay, and I only care about the right. So after all this circuit, I only care about the first outcome. I only care about whether this outcome is 1 or 0. Okay, so the probability of accept, or basically output 1, the probability of output 1 is just something. It's just the you can write down this projector. Let's say this projector is 1, 1. Okay, so let's call it pi 1. So it's just a simple projector where it's a psi pi 1 psi. Okay, so its probability is the expectation value, right, of this projector. Okay, so let's write this down. So it will be psi 0, u1 dagger, dagger, pi 1, dagger, up to u1 dagger, psi 0. And okay, so I can you can compute this by a set that inserts the identity. Okay, so insert identity means this. Okay, so this identity is just this. So quantum mechanics stuff. I recently find it doesn't, it's not important. Sometimes I will just murmur about my life. Okay, so keep going, and until you insert something, right? So you can keep inserting. So after inserting half, that you will spend n plus 1 of them, right? You get something here, yn plus 1, and yn plus 1, pi 1, and the yn plus 2, and keep going. So finally, you will get the y2n plus 2. So it's this, and the y2n plus 2 side 0. Okay, it doesn't matter. So all you need to know is that this is y1, y2 up to y2n plus 2. Right? So you have like all this middle identity. Okay, so this means that your results can be written as sum of y1 up to y2n plus 2, and each of them is belong to 0, 1 bit string with length of q to the n. Okay, so these are all the small results. So it's y2, u3, y3, and then y3, u4 plus. So y4, keep going. And finally is the y2n plus 2 and the y2n plus 2 side 0. And then there's a previous guy here. Okay. So notice that, so now I can imagine the probability. This is the probability of accept. I can imagine the probability of accept. Is the sum of this y1, y2 up to y2n plus 2. And there are lots of inner product here. Okay, so this is called sum over history. Okay, so you can see your accepting path is basically the sum of exponential. So the probability of accept is the sum of exponential path. And then notice that each path can be computed. So each path means that once you fix y1, y2 up to y2n plus 2, then each path can be computed in polynomial time. Probably not sure. Right? The reason is the following. Reason is that each of yi, uj, yi plus 1, right? This guy only act on 3 qubits. Right, so all of these guys exponential large, that you don't care, right? You only act on small 3 qubits. Okay, so this guy only act on small 3 qubits. You don't care. So you can compute this in polynomial time and also polynomial space. Okay, so that means that all of you have polynomial of them, you have exponential of them. Therefore, each one that you can only use polynomial time to compute. But most importantly, you can use polynomial space to compute, right? Because polynomial time, you can always use polynomial space. Okay, so you can reuse the space. It's the same as the NP complete problem, so you can reduce the space. Right, so you given some space, you use this space to calculate this, and then store this results into some place, and you also use this space and calculate again and store it. And then you at most have like 0, 1, q to the n, right? So all these store results at most have that q to, you only need the q to the n bit to store the results, and then you just compute sum of it. Okay, so simply speaking is that each pass you only need the polynomial time, this polynomial space, so you can reuse the space so that the probability of accept can be this BQP in the P space. Okay, so the hard part is to prove that BQP is a subset of PP. Okay, so PP is let me just recall the PP definition. So PP means that when X belongs to L, that basically what you're doing is that there is a probability algorithm, or a probability algorithm, or the probability machine, such that this probability machine, right? Say your probability machine output 0, sorry, the output 1. So output 1 is strictly greater than half. Okay. And if X do not belong to L, then the Turing machine need to output 0, strictly greater than half. And then this is the same as if x belongs to L, that this guy is yeah. So this is the same as if x belongs to L, the probability output 1 is greater than half, and then when x do not belong to L, the probability output 0 is greater than half, and this means that the probability of output 1 is strictly less than half. Okay, so this is definition of PP. Okay. So another way, let's say another way, because another way is important for our proof. So another way is to say the following, right? So I can define expectation value of the probability, right? So that means the output. So let's say I change this 0 to be -1. Okay, so why I can say the following. I can say if x belongs L, then I define expectation value to be the expectation value of the output. Okay, so it's the expectation value of the output, of the algorithm output. Okay, so if x belongs to L, then my expectation value of the output will be the probability. My probability output 1 is greater than half, right? So it should be greater than half plus something which less than 0. So this means that probability output 0 in this first case is less or equal to half. Okay, so that means that it's less than half, right? So it's here, let's say times -1. Sorry, it's this and times -1. Okay, so this is greater than you can show it. So this is 0. So what I'm saying is that if x belongs to L, then the expectation value of the algorithm output should greater than 0. So if x do not belong to L, the expectation value of the output should be less than 0. So in this way that I use the expectation output, I change 0 to -1. I change 0 to -1. So this is the very good way to check that where the algorithm is in PP. You can show that if your expectation value of the output is greater than 0, that's basically x belongs to L. If x do not belong to L, expectation output less than 0, you can use this way to show that this algorithm is in PP. Okay, so now let's go to a proof. So our main proof to show that BQP is a subset of PP. This proof is the most difficult one, and I think. Okay, so recall that in your algorithm that you have C0 and this kind of gate, Hadamard and this gate. And for each C0, right, then that you will like separate your computational basis into 2, and the CC0 will also do this. C0 will not do this, C0 will not do this, but your Hadamard gate, right? So if let's say you start with some 0, 0, 1, and then you do the Hadamard H3, then you will get something like this. And you can, if you apply the C0, maybe if you apply C0 1, 2, then you will get something, and you will get something. So each C0 or CC0 or Toffoli gate, you will not separate the path, right? But for each H, you will separate the path. So that means that you will get 2 to the H terms. So H is a number of Hadamard that you apply on the circuit. Okay. So I use P to label the final layer. So to label each final results, right? For example, if you're this 0, 0, 1, 1, 1, 0, showing the final layer, that I use P to represent this. Okay. Sorry, it's not bad. It's not a good thing. I use let's say I use label P, or I will use LP, just for the convenience. Okay, so each pass is so you can measure this as a computational tree, and for each pass I use label P to represent the final results. For example, this pass finally arrive at 0, 0, 1, then I will call LP is 0, 0, 1. Okay, so your final psi will be 1 divided by 2 to the h divided by 2, or summation of the label p. And then you can show that the sign, right? The sign will always be plus or minus 1. So let's use SLP. So SLP will define to be sine of p. So it's either plus or minus 1. Okay, so this is your p. And right, so I can write 1 divided by 2 to the h divided by 2, and the summation y belongs to 0, 1, q to the n, p, and l, p, y. So I collect the results. Whereas y is, I should use L, this one, and where S of p, and I collect this is y. Okay, so let's call it alpha y. Right, alpha y is amplitude, the amplitude you measure, and then you can see that alpha y squared. Say alpha y is basically this. So you consider all the paths such that L path L, the p will be y. Okay, so will be this, right? You square this, will be the S of p, S of p prime, and the p and the p prime, but such that L of p equals L of p prime. Okay, so this is your alpha y squared. Okay, so our goal is to use this to prove that there is a PP algorithm on it. Okay, so notice that we still have our pi 1. Okay, so let's say that let's compute the probability of this circuit, BQP circuit output 1 minus probability of BQP circuit output 0. Okay, so output 1 basically is the following, right? So output 1 basically means that alpha y squared. So you collect all the alpha y squared such that the first bit of the first bit of this y will be 0. Will be 1. Okay, so this is our y, the first bit, let's call it y1. So you sum over y. Let's use this. You sum over y such that the first bit is 0. Okay, sorry, it's 1. Minus your sum over y, and your first bit is 0. Right? Yeah, should be this. Okay. So I can write as this. So our y, and this is minus 1 to the identity, where y1 is 0. So this is bad notation. This means that when y1 is 1, then this is 0, right? Because this is identity function on y1 equals 0. So if y1 is 1, then this minus 1 to the 0 power is 1. So it's alpha y squared. When y1 is 0, then you get an extra minus sign. Okay. So this you can write as 1 divided by 2 to the h. And then you plug your SP and SP prime. Remember that alpha y is here. So you get the minus 1, minus 1, and the 1. And then your LP, right? LP is 1 is 0. And for this, you sum over P and P prime, and LP equals to LP prime. Okay. So what we are doing is this guy will be greater than 0 if x belongs to L. If x belongs to BQP, right? So this L is something is BQP. Okay, means that the BQP can efficiently solve it, right? So this guy is greater than 0. If x do not belongs to L, where it's not BQP, then this guy will be less than 0. Okay, so our goal is to construct the PP algorithm. Okay, so here comes the trick. So this trick is very weird. So the algorithm goes as follows. So you say you randomly sample to pass, you randomly pick to pass. So let's say you PNP prime. If you can compute the pass, right, in polynomial time. If LP is different from LP prime, the pass results different, then you just accept or reject with probability half. So this means that when they are different, then you just randomly choose your results. If LP is different from the same as LP prime, is the same as, then you just accept if what? If this guy is greater or equal to 0. Okay, you can compute this guy, right? Because you can compute it polynomial time. Okay, so one of these where LP1 is 0. Okay, so you just accept if this. Okay, so one now. Okay, so this is algorithm, right? So you need to show that the expectation value of its algorithm will greater than 0 if x belongs to L. Why this is true? By definition. Okay. So this is what we are going to show, right? But this is somehow like stupid, like trivial, right? Because why? Because the expectation value of this, we are going to show that this expectation value of this algorithm is greater than 0 if x belongs to L. Okay, but the expectation value of this algorithm, the output, if they are different, right, it will output the probability accept or reject half. So this one will cancel. So, and this guy, if this guy is the same, then I will accept that with this sign. But by definition, right, this sign, the sum of this sign is greater than 0, right? So it means that if x belongs to L, then sum of all this sign is greater than 0. That means that this algorithm will accept in half of the case, right? At least beyond half of the case, because I already know that this guy is sum of greater than 0, right? So the expectation value of this algorithm will output will be greater than 0 since at least half of the case. The half of the case that this SP and SP prime, this guy will be at least greater than 0. So at least half of the case that this sum will be greater than 0, right? Otherwise that this sum will not greater than 0, right? Because this guy is BQP, right? If x belongs to BQP, then this guy will be greater than 0. Then this sum will greater than 0, right? So I will have the at least half of probability that this algorithm will output yes. Okay. And the same trick that you can show if x do not belongs to BQP, that means that at most half of the case that all this will be less than 0. So it means that your algorithm will have an expectation value algorithm. The expectation value algorithm will less than 0 if you change output to be -1. Okay, so this is the proof. Basically similar as the NP proof. The NP is subset of PP. Okay, so that's it. So see you guys in the next videos.